Good morning, class. Today we'll talk about inverse functions. And before I even start, please, if you have a question, you can send a private comment or a class comment. But if it's taking me more than 10 minutes to respond to you, send an email because it's easier for me to see email notifications versus private comments from each of my Google Classrooms. So I hope you remember that inverse functions from 10th grade, 9th grade, and 8th grade, they've been talked about. An inverse function is simply the function that does the opposite. So if you have an input, and that input in that function gives you an output from one function, but if you have another function in which you put the output and then you get out the input, that is called the inverse function. So that's simply what the idea behind the definition of an inverse function. So it's basically a function that you end up where you started, or that does the opposite. An example is here. If I want to find the inverse of this function, f of x equals 3x plus 1, so this function takes x, multiplies it by 3, and then adds 1. Now, the inverse of this function, if you try to think about it, will be a function that takes x, subtracts 1, and then divides your answer by 3. I hope that makes sense. Like, if I put an input of, using this initial function, if I put an input of, say, 2, my output is going to be 3 times 2 plus 1, which is 6. So I need a function in which I will put 6, in which I'll put this 6 to get this 2. And as you can see from here, that function would be, and I'm going to call it the inverse function. This does not mean reciprocal. It's just the mathematical notation for the inverse of a function. It does not mean equals 1 over fx. So please don't make that mistake. That's not what it means. It means the inverse of a function. So anyways, continuing with this idea, if I'm looking for a function in which I will put this 6 to get back 2, then that function would take 3 times 2 plus 1 is not 6. My bad. 3 times 2 plus 1 is 7. Yes, 6 plus 1 is 7. So I'm looking for a function in which I will put 7 and I want to get out 2. That function, just like I kind of explained here, would take the 7. What is my problem with the 6? You take the 7, subtract 1, divide your answer by 2, which is 6, divide by 3, which will give you 2. So if you have a situation like this where one function takes the input and gives you the output, and then the other function takes that output and gives you back the input, then that function is called an inverse function. Now you might be wondering, how did I get this expression? If you're trying to find an inverse function, the basic idea is to try and make this x, try and make it the subject of the formula. Then when you manage to make it the subject of the formula, you replace this fx with x and replace this x with the fx. What am I saying? F of x, let me do it again here in green, just below here. So if f of x is 3x plus 1, what I want to do is make this x the subject, and then at the end of the day, I will just flip them and call this x f of x and call this f of x x. Alright, so how do I make x the subject? First, isolate the x. How do I do that? By taking the one that side. So I'll just have f of x minus 1 equals 3x. What else do I need to do to make x alone the subject? I need to divide by 3. So I end up with x equals f of x minus 1 divided by 3. And remember, at this stage, I just need to rename. Instead of this x, I will call it my inverse function, because this now would be the output and this would be the input. So I would call that my inverse function is equal to and then the f of x will now be the input, which is x for the inverse function. X minus 1 divided by 3. So that's simply how you find the inverse of a function. The idea is to make the x the subject. Here's another example. Again, I want to make x the subject of this expression. How do I do that? I'm going to cross multiply. So I'll have x times 1 is x is equal to f of x into x plus 3. If you don't want to keep writing f of x, you can just write y instead of f of x. You know that it means the same thing. It means the output. So actually, I'm going to go ahead and do that. I'm going to, instead of f of x, just write y, because y represents the output and x represents the input. But remember, you're trying to flip them such that x is the output and y is the input. That's basically what you're trying to do. If I expand this, this will be xy plus 3y. And remember, I want to isolate the x, so I'm going to collect like terms. All terms that have x, I'm going to take that term to the other side. It's going to be x minus xy is equal to 3y. I can factor out x because the objective is to make x the subject equals 3y. And then I'm going to divide both sides by 1 minus y. Divide by 1 minus y. So x ends up being equal to 3y out of 1 minus y. What I have done, again, to emphasize the idea of an inverse function, is I have changed the definition of this function from being that this is the input and this is the output to the fact that x is now the output and y is the input. And when I have it in that state, I can write my inverse function of x as 3x divided by 1 minus y. 1 minus x. I hope that makes sense. That's simply how you find the inverse of a function. So is every function going to have an inverse? What do you guys think? So not all functions are going to have inverses. Functions will only have an inverse if the function is a one-to-one function. What does that mean? This function is a one-to-one because it passes the horizontal line test. This one here passes the horizontal line test, means the horizontal line drawn on the graph of this function only cuts it at one point. But this one here is not a function because it does not pass the horizontal line test, because the horizontal line cuts it at two different points. Now you might be wondering why is that the case? Let's think of it like this. If I have a function that y is equal to x squared, then I asked you to find the inverse of that function, you would say, well, this is easy. The inverse of the function that would do the opposite of this one would be the square root of x, right? But remember, a function is supposed to take, for example, the function y is equal to x squared. If the input is -2, for example, if the input is -2, it should give me, let me rewrite it. If this is f of x equals x squared, and we have agreed that its inverse is the square root of x, if I put an input of -2 in this function, it should give me -2 squared, gives me an output of 4. An inverse function should be able to take this 4 and give me back, should be able to take an input of an input of 4 and give me an output of -2, because that's what an inverse function should do. So this inverse function of x should take an input of 4 and give me an output of -2. Input of 4, because the inverse function is square root of 4, that gives me a +2. Wait, what am I saying? Just excuse me for a second. Let me start over on this one. I want to use an example that will bring it out a bit more clearly. Sorry about that. So if my function is x squared, we know that its inverse function would be the square root of x. Now, if I put an input of 4 in this function, that input should be 4 squared, which would give me 16. Now, the inverse of this function should take 16 as the input and should give me an output of 4. So when I take 16 as the input, take square root of 16, instead of getting one output, I get 2 outputs, which is plus or negative 4, because you know that when you take the square root of a function, you get 2 values. So that is not a function. That is a problem, because this inverse function is going to 2 outputs, yet I have the same input that's going to 2 outputs, which is positive and negative 4, yet from the parent function, from the original function, I only had one input that was going to 1 output. So I hope you can see that if it is a 2 to 1 function, so a function like this would be a 2 to 1, where you have 2 values of x to 1 value of y, right? A function like that would not have an inverse over the whole domain of the function, because in this expression here, I have one input going to 2 different outputs. And I hope you remember that if that's the case, that's not even a function, right? So that's not a function. So even just by the fact that it's not a function, it cannot be the inverse function for this function. So in cases like this, if a function is a 2 to 1, just like we saw in this image here, if it's a 2 to 1, or if it doesn't pass the horizontal line test, it's not going to be a function. So going back to this f of x equals x squared, and its inverse being square root of x, inverse of x being square root of x, let me write that better. If the inverse of x is the square root of x, this function can be true for certain sections of this graph. If I restricted the graph of y equals x squared, because I know it's supposed to be like that, but if I restricted it to only the part of the domain from 0 onwards, if I restricted it to this domain, then it would have an inverse, because then I can use this inverse correctly and I wouldn't have a problem. I hope that makes sense. Graph of an inverse function. So when I'm graphing an inverse function, I just need to reflect the graph over the line y is equal to x. And I'll show you, again, going back to this example of f of x equals x squared, and its inverse equals the square root of x. So we have agreed that this one can have an inverse over the domain 0 to infinity. If I try to draw these two graphs, and I'm only going to draw this over the domain 0 to infinity. If I draw the graph of y equals x, it's going to look like this. However, if I draw the graph of y equals square root of x, I hope you remember from the parent function, that graph is going to look like this. Now what's interesting is that those two graphs are almost opposites of each other. Actually, it looks like they are reflected. That black line is supposed to be straight. It looks like they are reflected along the line y is equal to x. Now this is going to be true for every function that has an inverse. To find the graph of an inverse function, you will simply just have to reflect that graph over the line y is equal to x. We have an example here. How can I draw the graph of this function. First of all, I need to draw the line y equals x. After drawing the line y equals x, I can just reflect the curve. I can just reflect this section of the curve over the line y is equal to x. How do I reflect? I need to switch the input and output, or just flip the point. So for example, this point is 2, 0. Then on the other graph, it's going to be 0, 2. This point right here is x is 6, y is 2. What do you guys think it's going to be on the other side? X is 2, y is 6. Right? So what I'm doing is simply switching the x and y values. This point right here is x is 10, I guess y is 3. And then on the other side of the line y equals x, it's going to be x is 3, y is 10. So something like that. And then when I've finished plotting those points, then I'm going to sketch the curve that is a reflection over the line y is equal to x. So this is what is happening, because I hope you saw in this example that in this equation, in this part of the graph, I used 3 points. I used 2, x2, y0, x 6, y 2, and I also use x is 10, y is 3. So those are points that I read off of this graph. But then on its inverse, the points that I read off were x is 0, y is 2, and then x is 2, y is 6, and then finally x is 3, y is 10. I hope you can see that the x and y values are flipped. The x value of this one is the y value of that one. The y value of this function is the x value of the inverse, because the inverse takes the output of the normal function and gives you the input of that normal function. So to find the domain and the range of an inverse function, all I would need to do is to flip the x and y values. So to find the domain, just like you see here, if this is my function, this is the domain, this is the range of the original function. To find the domain and range of the inverse, I simply flip. That's going to be the domain of the inverse function, and that's going to be the range of the inverse function. Right, let's do some examples. The domain of f of x in this question is the domain of f of x are the x values right here. So put in x values -2, -1, 0, 1, and 2. And the range are the y values. When it comes to the inverse function, the domain are the flipped, the points are flipped. The domain now will be the y values of the function f(x), and the range will be the x values of the function f of x. I hope you can see that the domain and range are simply flipped or switched. Domain and range of inverse functions again. The range of a function is the domain of its inverse, and the domain of a function is the range of its inverse function. All right. If f of x is square root of x, find the inverse function of f of x. All right. So f of x, the inverse function of f of x is going to be equal to x squared. I talked about this earlier, but that's only going to be true if x is greater or equal to 0. I talked about this and I explained why that's the case a couple of seconds ago. If I graph f of x and inverse function of x, this would be my f of x. This is my f. This is the f of x right here, and this is my inverse of x right there. How do you do that? By reflecting the function f of x over the line y is equal to x. So how do you test if two functions are inverses of each other? It so happens that if two functions are inverses of each other, then the composite function f of g of x will equal to g of f of x, and both of them will be equal to x. Kind of, yeah, we're going to see some examples. We can start with this example, or let me start with something here that's a bit, if I have f of x equals x squared, I love this function, you guys love it too, and its inverse is equal to the square root of x over the range x is greater or equal to 0, and this is also x greater or equal to 0. I hope you can see that f of x should be equal to any x value that I put in here. If I take f of f inverse of say 4, what will that give me? Let's see. What's the inverse function of 4? Because remember, I start with the inside part. What's the inverse function of 4? That's going to be 2. And what's the f of 2? F of 2 is take 2 and square it, I get 4. I hope you can see that if two functions are inverses, then f of x should just equal to x. And that's what this description is. If two functions f and g are inverses, then f of g of x or g of f of x are going to equal x. And we have an example here. Let's try to find out if g is an inverse of f. Remember, if g is an inverse of f, then g of f of x is going to equal to x. So let's test this. If g of f of x, I will start with what's on the inside. That's f of x, which is right here. And then g of x says, take 1, divide it by x, which I have over here, and then subtract 2 from the answer. When you simplify that, you end up with x plus 2 minus 2, which is x. Let's check the other one. Is f of g of x also equal to x? F of g of x is 1 over x minus 2, and that's what I'm inputting in the function. So I'll have 1 out of 1 over x minus 2 plus 2, which is just 1 out of 1 out of x, which ends up as being x. So you can conclude that yes, g is an inverse of f. Use function composition to verify that fx and gx are inverses. Right. If you're using function composition, then this is what you're looking for. You're looking for if f of g of x equals g of f of x. Now, it's not going to be always the case that sometimes f of g of x is equal to g of f of x. For some functions, f of g of x might equal to x, and that's going to mean that it's a function, but it doesn't have to check the other one, g of f of x, to see if that's also equal to x. Find the domain on which each function f is 1 to 1 and non-decreasing. Write the domain in interval notation. Find the inverse of f restricted to that domain. Okay, so we're trying to find the domain on which this function is 1 to 1. If I graph this function, I hope you remember, it shifted 6 units to the right. That's simply what's happening to it. So instead of starting at 0, it's going to start at 6. And then go like this. And then go like this. Now I hope you can see that a horizontal line drawn anywhere on this graph will cut that line at 2 points for all values of x from negative infinity to infinity. But if I restrict my domain to start from right here, if I restrict my domain to start from 6 to infinity, then that function is going to be 1 to 1. Because if I have restricted that domain, then a horizontal line only cuts it at 1 point, right? So, over the domain 6 to infinity, this function is going to have an inverse, all right? And we can also now find that inverse by just trying to find, trying to make x the subject. So if f of x is equal to x minus 6 squared, I'm trying to find the inverse. Remember, I can call this y is x minus 6 squared. If I try to find the inverse, take square root both sides, I'll have square root of y equals x minus 6. And if I want to isolate the x, then x is equal to square root of y plus 6. And I can write it as an inverse function. F inverse of x is simply going to equal square root of x plus 6. This inverse is only valid for that domain of the function. If f of 3 is 2, find the inverse function of 2. What do you guys think? F of 3 gives me 2, then the inverse function of 2 is supposed to give me 3. Okay, inverse function of 2 is basically the definition of function, is supposed to give me 3. Again, if you have a question, send a comment. If I'm taking too long to respond to your comment, send an email. Bye.